Why the Tacoma Narrows Bridge collapsed in slow motion. Welcome back to Blueprint to Reality, where engineering theory meets real-world failure and innovation. On this channel, we don't just admire structures, we understand them. Today's video explores one of the most dramatic and educational failures in engineering history. Introduction. On November 7, 1940, a suspension bridge in Washington, USA, twisted, bent, and finally collapsed, all while cameras were rolling. This was not an explosion, not an earthquake, not even a storm. The Tacoma Narrows Bridge failed slowly, visibly, and violently, becoming one of the most important lessons in structural engineering. In this video, we'll break down what the Tacoma Narrows Bridge was, why it began to oscillate, the engineering mistakes behind the failure, and how this collapse changed bridge design forever. 1. The Tacoma Narrows Bridge. An overview. The Tacoma Narrows Bridge was a suspension bridge spanning the Tacoma Narrows Strait in Washington state. Key facts. Opened in 1940, main span of over 850 meters, extremely narrow and lightweight design, nicknamed Galloping Gertie, due to its movement in wind. At the time, it was one of the slenderest suspension bridges ever built. 2. The first warning signs. Even before the collapse, the bridge showed unusual behavior. Drivers experienced vertical bouncing side-to-side movement, visible waves along the deck. Instead of being stiff, the deck behaved like a flexible ribbon in the wind. These oscillations were initially considered harmless, a serious underestimation. 3. Wind and aerodynamic forces. Unlike earlier bridges, the Tacoma Narrows Bridge had solid plate girders, very shallow deck depth, poor aerodynamic shape. As wind passed over the bridge, pressure differences formed above and below the deck. Airflow became unstable, forces began feeding the bridge's motion instead of damping it. This interaction between wind and structure is known as aeroelastic behavior. 4. The real cause. Aeroelastic flutter. For years, the collapse was mistakenly blamed on resonance. But the real cause was aeroelastic flutter. Flutter occurs when wind energy continuously feeds structural motion. Oscillations grow instead of dying out, the structure becomes dynamically unstable. On the day of collapse, wind speed was only about 40 mph. The bridge entered a torsional oscillation mode. One side of the deck twisted up while the other twisted down. The motion increased until the structure could no longer resist it. 5. Why the bridge collapsed in slow motion. The collapse appeared slow because the bridge was highly flexible. Failure was progressive, not sudden. Structural elements failed one by one. As cables snapped and hangers failed, load redistribution became impossible. Large sections of the deck tore apart. The bridge finally fell into the water. The slow motion made the failure clearly visible and unforgettable. 6. Engineering mistakes that led to failure. Key design flaws included insufficient deck stiffness, poor aerodynamic design, lack of wind tunnel testing, overconfidence in existing design formulas. At the time, aerodynamics was not well understood in bridge engineering. 7. Lessons learned from Tacoma Narrows. This single failure transformed structural engineering. Major changes included mandatory wind tunnel testing for long-span bridges, aerodynamically shaped decks, increased torsional stiffness, integration of structural dynamics in design codes. Modern bridges like the Akashi-Kaikyo Bridge and the Golden Gate Bridge benefit directly from these lessons. Conclusion. The Tacoma Narrows Bridge did not fail because engineers were careless. It failed because engineering knowledge was still evolving. Its dramatic collapse taught the world that wind is not just a load, but a dynamic force. Structures must interact safely with their environment. Failure can be the greatest teacher in engineering. If this breakdown helped you understand one of history's most famous structural failures, like, share, and subscribe to Blueprint to Reality. Let us know in the comments, which engineering failure should we analyze next? Because at Blueprint to Reality, we don't fear failures, we learn from them. See you in the next video.